Okay, we need to finish our topic on digital data communications. We need to say something about the midterm, and then with the time left we'll go through some practice. We will not go through the answers of that quiz. That's some good study for you to look at the answers for that quiz. You may see some related questions in the practice exam. This is the exam that you have next week. At least this is the first page of the exam. First page. So the conditions are listed. Let's have a look. "17 pages. So this what I'll show you here will be available on the website. So I'll provide a link. So don't need to copy it down. 17 pages. Closed book. No dictionary. Calculator is allowed. Bring a calculator. A calculator is recommended. Okay? Normal things, normal. Okay, when we're talking about a sequence of bits, then in all cases in the exam and in fact in the lectures, I'm assuming that, where are we? The first bit is the leftmost bit. And the last bit is the rightmost bit. So we go left to right when we look at a sequence of bits. So if I say the first bit is in error, then it's this bit. So in this sequence of 0, 0, 0, 1, 1, 1, 1, the first bit is 0, the 8th bit or the last bit is 1. So just the notation we'll use is the first bit is the leftmost bit. Speed of transmission to speed of light is 3 by 10 to the 8 meters per second. That's given, and you use that whenever you need it. The free space propagation path loss model, the equation is given. You don't need to remember that. You didn't need it in the quiz, but you'll see that later. The antenna gain for a parabolic antenna, or in fact for any antenna, is given. Note that the area, AE, is the effective area. So it's not the physical area. If we have a circle, you can calculate the area, pi r squared. But the effective area is often a fraction of the physical area. I would give you what fraction it is. I would say, okay, the effective area is half of the physical area, or 1/3 of the physical area. I would give you that information. But just remember, the effective area is not necessarily the physical area. Lambda you can calculate, speed of light divided by the frequency. And that's all. There are 8 questions. Of course, it's 3 hours. Up to and including digital data communication techniques. Up to and including this topic. Hamming codes and so on, or Hamming distance and forward error correction. Of course, use the previous year exams and quizzes as practice. They will give you the idea of the types of questions. You'll see over previous years that the questions do not change much. Some they do. All right, the equations of free space and antenna gain are given. You saw that. You need to know the other things. One thing that you need to know, or you may need to know, I'm not saying that there's a question in it, but we mentioned with the digital encoding techniques, we had a list of 6 or 7. You should remember non-return to zero level and non-return to zero invert on ones. The others you don't need to remember the definitions. Manchester, bipolar AMI, pseudo-ternary, differential Manchester, HDB3. You don't need to remember how they work. But if I gave you a description, that is, Manchester, we have low to high for bit 1 and high to low for bit 0. If I gave you that description in the exam, you could answer a question on it. So you don't need to remember the details of these. as you saw in the quiz, you need to know what is shift keying, what is amplitude shift keying, what is phase shift keying, what is phase modulation, frequency modulation. You need to just know what they are. So if I gave you a picture, you could interpret what it means about those techniques. And that's all I can think of in terms of hints for the exam. 8 questions. The first question is a fill in the blanks question. So multiple parts. All questions have multiple parts. The first one is a fill in the blanks. That is, there's a phrase or a sentence with a blank space. You need to select a word to put in there. And I give you the words to select from. That is, selecting from these 50 words, fill in the blank space to make the sentence correct. The remaining 7 questions are calculation questions asking about concepts. Any questions about the exam? Now's the time to ask. Any questions? How are you going to study for the exam? What are you going to do over the next few days? You're going to use previous exams. Quizzes. Have a look at the previous year's exams on the website. So this document will be on the website, or in fact already is. Okay. We need to finish on digital data communication techniques. So let's hopefully spend 20 minutes to finish this. So what we've seen yesterday is that we can have schemes for error detection. Transmitter sends a sequence of bits. Receiver receives a sequence of bits. It wants to know if there are any errors in the received sequence. We saw the very simple case of a parity check as an error detection scheme. If we detect an error, if I send something to you and you detect an error, one approach to fix it is to ask me to send again, to retransmit. We haven't covered that. We did cover the approach called forward error correction, where the transmitter sends extra or different information. Let's go back to this slide. This is the general process for forward error correction. We went through an example. The general process, the transmitter has some data, k bits of data to send. We use an encoder, a forward error correction encoder, to map or to encode that data as a code word. We saw the encoder in our example was that table. 2 bits of data became 5 bits of code words. That's the encoding process. Instead of transmitting the data, we transmit the code word, which represents that data, the n-bit code word. The receiver receives a code word and then uses the decoder to try and get the original data back. If there are no errors, we'll get the original data. If there are errors, we may detect them, and in some cases we can correct them. In some cases we cannot. That's the general process. Let's make sure you understand the Hamming-based forward error correction and give you one more example. We went through 3 examples with this forward error correction encoder. Try one more. The same scenario as we had yesterday. We have data to send. the transmitter has data, it encodes that data into a code word. And in our example, we have 2 bits of data and a 5-bit code word. The encoding is simple, just look up the mapping. What I want you to do in the next 3 minutes, consider the case where that's the transmitted data, 01, hence the corresponding code word. What happens if the last 3 bits are in error? You transmit this over the link, the last 3 bits are in error. What is received and what does the receiver do? Quickly solve that. So try and remember the steps for the receiver. What's the code word received if the last 3 bits are in error? And then what does the receiver do with that received code word? Anyone got the answer? What's the received code word? What's the received code word? Transmitted code word 00111. The link has some errors, and in this case the last 3 bits are in error, so the received code word will be the last 3 bits are in error. Okay, so the transmitter sends this across the link. The last 3 bits are in error. There's an error across the link, or errors in this case. Therefore, what's received what's the receiver do now? So this is what the code word is that it has. What is our receiver going to do? It needs to check that code word against the valid code words, where the valid code words are the ones we expect to receive, these 4. We know the transmitter will always send one of these 4. It's just that if there are errors, what we receive may be different. So when the receiver receives a code word, it checks, is that code word received valid? Is this one valid? Yes, it matches the first one. If it's valid, then the process is simple. Then we assume that that's the received, that was the transmitted code word. We assume that there were no errors, and we do the decoding. The decoding is to take the code word and to determine the data. If it's valid, then we simply look in the table. Received code word is this. It matches this one. The data must be 00. It's finished. Is that good? Why is it not good? Because the data is different at the transmitter and receiver. The original data at the transmitter was 0 and 1. The receiver thinks the data that was sent was 00. That's obviously wrong. We've got a problem here. As with error detection cannot detect all errors, error correction cannot detect and correct all errors. It's not perfect, and this is an example. The problem is that we've got 3-bit errors, and we're unlucky in that the 3-bit errors have changed the transmitted code word, which was valid, into a received code word which is valid but is different. We were unlucky, this was transmitted, this is received. As a result, the receiver thinks everything's okay, it's not, and we get the wrong data. So if that was a 4th example, the previous 3 examples we went through yesterday, the first case was simple, there were no errors. the first example we went through yesterday, which is on the next slide, there were no transmission errors. Data was received okay. That's what we want. The second example we went through, we had errors and they were detected and corrected. We saw an example when I think we transmitted this code word, the middle bit was in error. We still got the original data. That was a case that we knew that there was an error and we fixed that error. And the receiver still got the same data. So that's another case that can occur. Error can be detected and corrected. The third example we went through yesterday, it's the example 3 on these slides, was an error was detected but not corrected. That was the case where we received an invalid code word, we compared it to the 4 valid ones, and there were 2 that had a minimum Hamming distance. I think from memory, when we compared it, the Hamming distance between these code words were 3, 2, 2 and 3. Because 2 valid code words were close or the same distance to the received one, we could not correct. We knew there was an error, but we could not fix it. So that's another possibility. And the fourth possibility, which we see here, is that we can say the error is missed. We transmit, there are errors. The receiver doesn't know that. It doesn't realise there are errors. That's a bad outcome. Ideally, we'd like no errors. If there are errors, I'd like to be able to detect them and correct them. But in some cases, if I can't correct them, at least detecting them is okay. The worst case is if I miss the errors. We don't want that to happen. Different algorithms for error correction have different capabilities as to how often those 4 cases occur. We'd like to maximise the first cases, 1 and 2, minimise case 4. So that's how the different algorithms compare to each other. We've just gone through one algorithm using Hamming error detection. There are many others. Any questions? Okay. Okay now? If I gave you a surprise quiz now, would you answer a question on Hamming code? Error? Some people yes, some people no. Quiz. Yes? Okay, quiz question then. If the quiz question was, okay, we have this scheme, how will you make it better in terms of error correction capabilities? Using a Hamming-based error corrector, how would you improve the ability to correct errors? We saw an example here where we missed the error. How would we reduce the chance of that happening? We're not retransmitting, we're just doing forward error correction.
Can we
Transmit
transmit 2 code words?
2 code words. How would I've only got one piece of data. What do you mean, transmit 2 code words?
If you have the 0, 0 data, can we transmit the code words for the first and the second one?
Transmit both code words. I don't know how you would implement or what the purpose of that is. But you're somewhere on the right track. maybe. A longer code word. Here our code word is 5 bits. The problem that we saw here was that when 3 bits changed, 3-bit errors, we had one of the valid code words, actually it was this one transmitted, 3 bits changed, turned into this one. That was the problem. So in fact the problem arises or it will arise more often if the valid code words are close to each other. What's the Hamming distance between these two? 3. They're 3 bits different. What if instead of this scheme the first code word was not all zeros, but the first code word was this? So replace this with this. Do you think that's good? Which one's better, having the first code word as all zeros or as 00110? This one is worse. Why? Because it's closer to one of the other code words. What that would mean is if we transmit this and there's just 1 bit in error, the last bit, we would receive a valid code word and we'd make the same mistake again. So what we'd like is that the valid code words are different from each other. That is, they have a large Hamming distance between each other. Between this one and this one, this one and this one, and so on, and between all combinations. So when you design the table, you do not choose the code words randomly. You should choose the code words such that they are large Hamming distances from each other, so that even if there's a small change in this one, that is 1-bit error, the receiver will not receive another one and make a mistake like we did here. If we increase the length of the code word, we have more opportunities to have a larger distance between the valid code words. If our table was something different, it was if we have a 10-bit code word, 2 bits of data, 10-bit code word, we can do this. Now we have how many possible code words? 2 to the power of 10 is 1024. 1024 possible code words. We need to choose 4 of them to be valid. This may be one of them. Another one would be chosen to be significantly different from this one. And then the third code word would be chosen to be different from those two. That is, that we'd like to choose code words which have a large distance between them. And the more bits we have, the more chance that we can do that. Maybe look at the other way. What if we only have a 3-bit code word? A smaller code word. Then we need to choose another code word. We've got 8 to choose from. Here's one, maybe the other one. Let's say they are the 4 code words. If there are 2 bits in error, if we transmit this, there's a chance we get this one or this one, and our receiver would make a mistake. That is, if there are 2 bits in error, there's a chance that the receiver would be incorrect. The less bits we have in our code word, the more chance that the receiver will make a mistake. And the other way, the longer the code word, the better the error correction and error detection capability. I think we'll go to the last slide, and it summarises some of these points. Okay, so our aim is to detect and correct as many errors as possible. We know in practice we cannot detect and correct all of them, but as many as possible is our aim. Both error detection and error correction, we send more bits than the original data. In our case, we had 2 bits of data and sending 5 bits of code word. And with our error detection, we added 1 bit of parity. So we send more than the original data. We have k useful bits of data, k bits of real data, but we transmit n bits. So in general, we can say the efficiency is k divided by n. Recalling back to our parity check, our 1-bit parity check, we had 7 bits of real data and 1 bit of parity, so we had 8 bits in total. For every 7 bits of real data, we transmitted 8 bits. So our efficiency was 7/8. With our example error correcting code, FEC, we had 2 bits of real data and we transmitted a 5-bit code word. That was the example we went through in the slides. Therefore, the efficiency is 2 out of 5. For every 5 bits of data we're sending, only 2 bits are real or are equivalent to real data. So, to increase the efficiency, we need to increase k relative to n. But in terms of error detection and error correction capability, increasing n, if we fix the number of bits of real data, if you make n larger, we can detect and correct more errors. 2 bits of data, 10 bits of code word, we can detect and correct more errors than 5 bits. Increasing n increases our error correction and error detection capability, but increasing n decreases our efficiency. If we had k equal to 2 and n equal to 10, efficiency would be 2 out of 10. That's a decrease compared to here. But we could detect and correct more errors. So when people design error detection and error correction algorithms and select them, they need to consider the values of k and n. What's the best trade-off? High efficiency, but we also want to detect and correct many errors. It depends upon the links that they used over. Go back to our forward error correcting code where we had 2 bits of data, we had a 5-bit code word. If we were using this over a link which had a data rate of 1 megabit per second, if there were no errors, what's our throughput? Using forward error correction, the example we used in the slides, 2 bits of data, 5-bit code word, using this over a link which supports 1 megabit per second, what's our throughput? Calculate the throughput. This is practice for the exam. You cannot take your laptop or your tablet into the exam, so I suggest you try on a piece of paper. Got an answer? Throughput is the rate at which we receive the real data. Look at the efficiency of this scheme. 2 bits of real data. For every 2 bits of real data, we send a 5-bit code word. How fast are we receiving real data if there were no errors? Have an answer? Have an answer? You've got the question. What do you think the answer is? Someone's on the right track. Answer? For every 2 bits of real data that we send, that we want to deliver to the destination, we in fact send 5 bits of code word. So if I had 1 million bits to send of real data, or 2 million bits of real data to send, I'd need to send 5 million bits across the link. For every 2 bits, transmit 5. The throughput is the measure at which we receive the real data. The data rate, 1 megabit per second, is the speed at which we can send the bits that need to be transmitted. So, as we've got over here, our efficiency is 2 out of 5, 2 over 5. Two-fifths of our data rate is used for delivering data. I'll write that clearer. For every 1 million bits we send, 2/5 of them represent real data, which is 400 kilobits per second. Another case, if we had a 4-bit code word. To transmit 2 bits, I actually transmit 4 bits. We're 50% efficient. I have to send double of my real data if I'm using such a code word. So of my data rate of 1 megabit per second, if we had two bits of real data, 4 bits of code word, we'd be delivering at half of our data rate, 500 megabits per second. The same applies with error detection, this concept of, okay, if it was using error detection, 7 over 8, it would be 7/8 of our data rate. Any questions about the efficiency of error detection and error correction? So we have two factors that we care about. We care about the efficiency and we care about the ability to detect and correct errors. And there's a trade-off between them. Increasing n increases our ability to detect and correct errors, but it lowers the efficiency. And that's all we have to talk about for error correction, error detection, digital data communication techniques. Any questions about this before we go through some other examples? Question? It's all right. K and N come from the error detection or error correction scheme. If I said in the example here, this information would be given, for example. From this, you know that K equals 2, because there's 2 bits of data, and N equals 5, because it's a 5-bit code word. That's where K and N come from. Or if I told you a 1-bit parity check on every 7 bits, you would know that K equals 7 and N equals 8, because we have 7 bits of data plus 1 bit. That's where the K and N come from. Any other questions? Any questions? Any questions here?
If use this method and throughput is
Okay. So let's go back to our parity check. In this example, we had a character and we used a single bit parity check, although the question doesn't say a single bit. We've assumed a single bit parity check. First, we needed to know how to map that character into bits. And I would have to give you, for example, the ASCII table, or I'd tell you that the character S maps to a sequence of 7 bits. So the data in this case is 7 bits in length. With the parity check, error detection, we take our 7 bits, we attach 1 bit of parity. So we have 7 bits of real data, K equals to 7, 8 bits to be transmitted, N equal to 8. And then you use the same approach. The throughput, if it would be 7/8 of the data rate. If the data rate was 8 megabits per second, and we were using our 1-bit parity check, it'd be 7 divided by 8 times by our 8 megabits per second, which is 7 megabits per second. So in these simple cases, the throughput is simply the efficiency times by the data rate. The efficiency is simply the number of bits of real data, K, divided by the number of bits we transmit, N. I think in the back of your handouts you have last year's exam. Try and find it. Last year's exam, question 1, draw the TCP/IP stack. Remember those 5 layers. What are the 5 layers? From the bottom up. 5 layers. You've got it on your... You've got the answer, but you'll remember that. Okay, it's on the front of your handout. Physical, data link, network, transport, application. The 5 layers of the protocol stack. This is going back to our first lectures. Addresses. This is about what capabilities are in each layer, what type of addressing. An IP address. What layer? And the hint here, okay, an IP address is used by IP, the Internet Protocol. What layer does that correspond to? The network layer. The network layer is about getting data across a network, across an internet, and the Internet Protocol does that for us. So an IP address corresponds to the network layer. What would you say an email address corresponds to? It's an application. It's specific for an application. Application layer. This, I don't know if we called it an IEEE address, but the 48-bit MAC address, the hardware address. The hardware address that when I buy my laptop, it comes with a hardware address. I do not change it. It comes with that piece of hardware. That's for communicating across a link. Hence, we can say it's part of the data link layer. I'd also accept the physical layer, but data link layer. Port number. What's a port number used for? It's part of the transport layer. What's it used for? How would you describe a port number? Yeah, a port number is used to identify an application, or more specifically an application process, to identify an application. It's in fact part of the transport layer. So the transport layer knows which application to deliver the data to. We'll just quickly go through some of these in the last 15 or so minutes, just to give you a feel of the types of questions. We may skip some. We won't go through all of this question. Here's a signal given as an equation. Draw that signal in the frequency domain. In fact, it was missing... I think in the original exam it was missing sign, but in this case it's okay, I've fixed it. How many components in our signal? 4 components. Frequency of the first component. Try and find the frequency of each of the components. First component, so remember to find the frequency, an equation that you should memorize, is a general equation for a signal or a sinusoid you should know the general format for a single sinusoid component. Peak amplitude sine 2 pi ft plus the phase. If you know that, then you can find in each component what is the value of f. The first part is 3 sine 2 by 10 to the 7 pi t. Amplitude equals 3, phase equals 0, and the frequency 10 to the power of 7. Which is 10 by 10 to the power of 6 hertz, or 10 million hertz, 10 megahertz. 2 pi f equals 2 by 10 to the 7 pi, therefore f equals 10 to the power of 7. So that's the frequency of the first component, and we can do similar for the other components. 6 by 10 to the 7 would give us a frequency of how many megahertz? How many? 6 by 10 to the 7 gives us a frequency of how many megahertz? How many megahertz? 30 megahertz. Good. Next one. 1 by 10 to the 8. 50. 1 by 10 to the 8 is 100 million. Divided by 2 would be 50 million. 10 megahertz, 30 megahertz, 50 megahertz, and 70 megahertz. So once we know the frequencies of each of the components, our plot in the frequency domain, we have impulses at each of those frequencies with an amplitude of each component. First component had an amplitude of 3. Second component has an amplitude of 1. .6 and .429. That's our answer for 3 marks in your exam. So to get started, you need to know this. And then find the individual frequencies and draw the plot. $10 megahertz, 30 megahertz, 50 megahertz, 70 megahertz. What's the fundamental frequency of that signal? 10 megahertz. Why? Why did you say 10? 10 is correct. They're all multiples of 10 megahertz. That is, those 4 components, this is 3 times this one, so they're all integer multiples. 3 times 10, 5 times 10, 70 times 10. If we have that pattern, then we can say the frequency of the overall signal is that 10 megahertz. The frequency of our signal is 10 megahertz. That's only, we can only calculate it in that way if they're all integer multiples of one of them. If they're not, then it's not so easy to calculate. And once you know the frequency, you can find the period. The period of the signal is 1 divided by the frequency. 1 divided by 10 million is 0.1 microsecond. So, all right, some things, they sound obvious, but people always forget for the exam. Know your units. Include your units in your answers. You'll lose marks if you don't include the correct units. And know the prefixes, mega, giga, micro, milli, and so on. So if the question says the frequency is 10 megahertz or 10 MHz, know what that means. 10 million hertz. Try another question. This is related to, it's much more complex, but related to your quiz question you just had, question 1. Let's try and explain that. Don't worry about reading the details of this question. I'll explain. We won't try and answer it, but we'll explain the concept used here and the concept used in the first question of your quiz. Our wireless transmission model. We have an antenna, a transmit antenna. We send a signal and it's received by the receive antenna. So look at our signal as it flows through the system. The signal strength is denoted by the transmit power, PT. We transmit a signal with a power PT. So let's say the signal is at some strength. An antenna introduces some gain into the signal. And we denote that by the gain of the antenna. So one way we can think of this is that if we have an original signal with powers of PT, the antenna amplifies that signal. A gain increases, a loss decreases. If I had to draw that, let's say the signal coming into the antenna is like this. With some gain, the signal coming out is larger. The gain increases the strength of the signal. So, we have some signal with a strength PT coming in. The antenna introduces a gain into the system, increases. We know across our wireless link the signal gets weaker. That's attenuation. We start out with some signal strength, it gets weaker over distance. The amount that it gets weaker between here and here is the loss. How much power do we lose between transmitter and receiver? The loss, or simply L. Start with a signal strength of PT, increased by the gain of the transmit antenna, lose by the amount designated for the loss of that link. When it's received at a receive antenna, that also has a gain. That increases the signal. Actually, draw it better. The result is the receive power. So, in summary, input transmit power amplified by the transmit antenna reduces over the wireless link. The amount it reduces is the loss, increased at the receive antenna, and the resulting value is the receive power. The loss, the free space propagation model gives us an equation for calculating the loss. But like in your quiz question, I told you how much the loss was. L is, say, 100 decibels. And I told you the gain of the transmit antenna. Gain and loss. Gain is a multiplier. Loss is a divider. If we have a gain of 2, then we double the strength. If we have a loss of 4, we divide by 4. In absolute values. In decibels, because we take the logarithm, and this is an important part and you needed to work out for the quiz, in decibels, because we're using a logarithm, multiplication becomes addition. The log of A times B is the same as the log of A plus the log of B. As a result, if we're using decibels, we start with a transmit power. We have some gain that increases the signal strength. If this is measured in decibels or dB watts, and this is in decibels or dBi, we lose power across the wireless link. That's a loss measured in dB. We gain at the receiver measured in dBi. The result is the received power measured in dB watts. If the values are in decibels, we can add and subtract. Add the gain, subtract the loss. If the values are in absolute numbers, then we multiply. PT times GT times GR divided by L equals PR. This is if we're using decibel values. This is if we're using absolute values. And this is very similar to our free space propagation model, where L equals this 4 pi d squared over lambda squared. In the quiz question, I gave you what L was. So you didn't have to know what 4 pi d over lambda squared was. You had the value, but in decibels. Converting to decibels can make the calculations very simple because you just add and subtract. And hence, quiz question 1 was the simplest of the 3 questions. It was add and subtract 3 or 4 numbers and you got the answer. The hardest part was knowing how to get there. That was the hard part. If you don't understand how to go from this in the absolute value to this, then take the logarithm of both sides and multiply by 10. Log of all of this times 10 should equal 10 log PR. That is, take the logarithm of this side, multiply by 10. That's how we convert to decibels. Take the logarithm of this side, multiply by 10. And because log of 2 numbers, the log of A times B, we can expand to be the log of A plus the log of B. That's a property of logarithms. So you can expand this out and you'll get 10 log PT, which is equivalent to the power in decibels, plus 10 log GT, which is equivalent to the gain of the antenna in decibels, minus 10 log L. So if L is given in decibels, that's the value. 10 log, the absolute value equals the decibel value, and so on for the rest. You'll see, I think, in that the answer to that question in the exam, and even in past, maybe past quizzes and past exams, there are more detailed, or shows you the exact formulas for doing that. And you'll see in the answer of the quiz how that's done. I think we've run out of time, so it's up to you over the next few days to check the quiz answers, which should be posted Thursday, because after the CS students take the quiz. And of course, you're already studying past exams, because your exam for this course is when? You'll find out. Okay, enough for today. I'll see you at the exam. If you have questions in the meantime, come and see me in my office or send me an email.